Welcome to the lecture series on numerical methods, finite difference approach. And in this lecture, in the last class, we have discussed that how we can just approximate this differential approximations in a finite difference form with these polynomials. And in this lecture, first we will just go for this like one-sided approximations, how we can just treat the polynomial in a one-directional sense, considering different points, that we will just discuss. Then we will just go for this solution of parabolic equations. In this form, we can just discuss different approaches like explicit approach, implicit approach, or Crank-Nicolson approach to find the solution for parabolic equations. First, we will just go for this explicit method. And if you just go for this one-sided approximation, the finite difference approximation for first order derivatives along the boundary can be obtained by using forward difference, which is of first order accurate. Especially if you just see like forward difference approximation if you are just using at a single point, suppose. So if you just see, so that we are just writing in the form like if you will have 2 points, especially if you are just considering like xi and xi plus 1 here. So then especially we are just writing this function as like f dash of xi as f of xi plus 1 minus f of xi divided by h here. And if we want to fit this polynomial with this approximation here, especially we can just assume a function as in the form of like f of x equals to a plus bx plus cx square here, a second degree polynomial, or we can just say it is a quadratic polynomial here. And at each of these grid points, suppose if you are just starting the boundary I equals to 1, then we will just consider consecutive 2 points, that is suppose I equals to 2 and I equals to 3 here, and each are spaced at equal distances like del x distances each. Then at each grid point 1, first suppose at first grid point we can just consider x equals to 0 here. Then at the I equals to 2 we can just consider this is as del x here, and I equals to 3 we can just consider x equals to 2 del x here. So at the first grid point, if you will just approximate this function, that is for x equals to 0 here, so which can just provide you as f equals to a plus b into 0 plus c into 0 here. So especially if you just see that at point I equals to 1 here, so f1 equals to a here. And for grid point 2, suppose if you just see here x equals to consider as del x here, and if we will just approximate this point with this function here, that function can be represented as since we are just putting the subscript I as fi here, so I equals to 2, so that is why we can just write it as a plus b delta x plus c del x whole square. And at grid point 3, suppose if you will just find this function, that can be written in the form of like f3, this equals to a plus 2b delta x plus c 2 del x whole square here. So if you will just go for this solving of these expressions like 3 equations, we will have 3 unknowns there. So if you will just solve these equations, then first from the first equation we can just get this coefficient a as f1 here, and b if you will just calculate, that can be represented as minus 3f1 plus 4f2 minus f3 by 2 del x, and c especially we can just find it as f1 minus 2f2 plus f3 by 2 del x whole square here. So why we are interested in this like one way of transformation is that, or one-sided approximation is that, sometimes in physical problems, if suppose some physical behavior is occurring inside the system which considers the property at the boundary, but this property is transmitting towards the inner points, then we have to consider inner 2 points considering with the first point to find the flow properties or to find the physical behavior of the system. So that is why higher order approximation it is needed to get more accurate solutions. So that is why we are just considering this formulation as in the form of like a plus bx plus c x square for the polynomial approximation to approximate these 3 different points at a particular time. So now if you will just approximate this first order derivative here, then we can just write del f by del x, that is nothing but b. So b especially if you will just see, it is nothing but minus 3f1 plus 4f2 minus f3 by 2 del x here. So, if you just see here, so 3 different points I equals to 1, I equals to 2 and I equals to 3 all are involved for this like first order differentiation here. Even if sometimes if you will just see this boundary conditions we are just treating as this normal boundary conditions, that is normal derivative equals to some certain value or 0 if we are just considering, then this normal derivative sense we are just considering the first order derivative there, and if we want to include all these fluid properties or like physical behavior properties there, so then we have to consider like 3 different points at a particular instant or in a particular subject, then at a time we can just write this formulation as in this form here. So, if you just go for like second order derivative here, though we can just differentiate that one, this function that is defined as in the form of like if you just see a plus bx plus cx square there. So, that is why it will just give you 2c there. So, 2c means c has a value there, that is in the form of if you just see f1 minus 2f2 plus f3 by 2 del x square here. So, 2 can cancel it out. So, that is why it can be written in the form of like f1 minus 2f2 plus f3 by del x whole square here. So, these approximations can be used for first order or second order differentiation in a one way approach or in a one sided approximation we can just write. Especially this is very useful whenever we are just considering any physical problem and which can be used along the boundary levels. So, after then we will just go for this methods for solving parabolic equations. And in the beginning of this lecture we have discussed this classification of partial differential equations. So, when we can just say that the differential equation is like parabolic in nature, hyperbolic in nature or elliptic in nature. So, if you will just see that if you will consider like one dimensional parabolic equation, it can be written as like del u by del t equals to del square u by del x square, where you will have this boundary for this problem. That boundary is defined at x equals to 0 and x equals to L here, and this time always it will start from 0 and this computation will go for t greater than 0. Suppose along the boundary, if the boundary conditions are prescribed for both the ends, either at the initial level. So, initial level means we can just consider that as like t equals to 0 here, that is nothing but u of x 0, which is defined as f x here, that is the initial condition. And if you will just go for this boundary for particular times or with variation of time also, we can just consider that the boundary value remains same or it will not get changed with respect to the computation, since we will just do this computation fixing these boundary conditions. So, that is why these boundary conditions are given as like u of 0 t as u0, that is nothing but a Dirichlet condition here, and u of Lt as ul here. So, to solve this problem we first discretize the domain into regular mesh such that xi equals to I del x here. If you will just define a domain as in the form of like you will have two boundaries here, that is one is defined at x equals to 0, other is defined as x equals to L here, and initial time level t equals to 0, all the values are supplied here, and as time proceeds then we can just go like t equals to 1 here. For t equals to 1 we have to consider like a boundary condition whatever existing here, here and here, we will just get the next point here, or we will just get the next point here, we will just get the next point here, we will just get the next point here. So, that is why first we have to discretize this domain into regular mesh or regular intervals. So, for this we will just divide this domain into like regular intervals here, and in this regular interval each of this interval can be defined as a del x, del x, del x, or some space length as h, or you can just define in your way. So, if you just discretize this domain in this form, then you will have these points like a starting point if you just consider as a 0 here, then the first point will be x1, second point x2, third point x3, likewise it will just continue. And each of these distances it can be computed, since x0 will be started at like x0 equals to 0 here suppose, then x1 can be written as 0 plus delta x, that is nothing but delta x, then x2 can be written as like x1 plus delta x, that is nothing but 2 delta x. So likewise, if you will just define here, then finally we can just find this xi, any arbitrary point, we can just write as xi minus 1 plus delta x here, and especially if you will just see, this is nothing but I delta x. So if we can just define this domain by putting all these nodal points, that is in the form of xi's here, which are placed at equal distances and which can be written as like xi equals to I delta x, I equals to 0, 1, 2 up to n, where x0 equals to 0 and xl equals to n. If we are just considering here, we will have these values of uij, that is j represents here the time level and I represents the coordinates for x direction here. So we can just compute these values at each of the increment of time levels, that is nothing but t equals to tj here, which can be written as like if del t is the space of time here. So for the first interval we can just write t1 equals to del t here, and t2 we can just write 2 del t here. So likewise we can just proceed, and obviously j has no restriction, so that is why you can just write j equals to 1 to up to a convergence state level, that where we can just find a steady solution there, or up to that level that we will have a converged solution. So based on this problem, if you will just go for this like explicit method here, so first we will just discretize this equation at mesh points, that is at ij point suppose, such that the time derivative is replaced by a forward difference and the space derivative is replaced by a central difference approximation here. So if you just go for this time derivative by a forward difference approximation here, we can just write, since forward difference approximation always it is just written in the form of like f of f dash of xi as f of xi plus 1 minus f of xi divided by delta x, and at the time level, since we are just considering this forward time level here, that is written as a del u by del t here. So del u by del t, this can be written as like u of xi means your I direction, we are just doing this derivative in the j direction here itself. If you will just see, del u by del t means time space, it is just getting changed. So that is why we are just writing I is fixed here. So u of xi tj plus 1 minus u of xi tj by del t here, which can be written as like del square u by del x square. This is nothing but del square u by del x square here, where we can just consider time level is fixed, since this variation is just coming, or this partial derivative we are just considering this has a variation in the x axis itself. So x axis means we can just consider this central difference scheme at 3 different points in the x direction, that can be considered this point as I minus 1, I and I plus 1 here. Hence this central difference approximation can be written as u of xi minus 1 j minus 2 u of xi tj plus u of xi plus 1 tj by del x square, plus this order of approximation. If you will just see, this left hand side order of approximation is a order of delta t here, and if you will just see this central difference approximation, it has this order of approximation that is in the form of order of delta x square. So that is why in a combined form, both the sides we are just putting it as order of delta t plus order of del x square here. And once it is written in this form, then we can just write this formulation as in the form of u I j plus 1, since in the next time level we are just computing. If you will just see here, so this level we are just computing these values. If you will just see j plus 1th level, this means that t equals to 0th level, all the values has been supplied, and we want to compute these values at the 1th level here. Since boundary values it is given, so these two values it is provided to us. So then we will just compute this next level values. So that is why ui of j plus 1, this is nothing but uij plus del t by del x square, since del t is multiplied here over. So del t by del x square into ui minus 1 j minus 2 uij plus ui plus 1 j. Especially we are just writing ui plus 1 j means that is nothing but u of xi plus 1 tj here. And then if you will just multiply del t, also del t can be multiplied, also this order of approximation here. So, that is why this is written as del t into order of del t plus order of del x whole square here. Let del t by del x square, suppose if you will just consider it as r, suppose. If you will just consider this as r here and neglecting all the error terms, we can just get this formulation as, since u I j plus 1 it is just written, then we are just writing this del t by del x square is equal to r here. So, r into u I minus 1 j, and then 1 I plus 1 I j is there. So, that is why 1 minus 2 r into u I j, then next is r u I plus 1 j, where this higher order terms is neglected here, and thus the value of u I j plus 1 can be computed explicitly. Since we are just involving this, if you just see here, that is I plus 1 j value is involved here, I j value is involved, I minus 1 j value is involved here. But all these time levels, if you just see, these all are at 0th level for the 1th level calculation here. This means that if you just see this slide here, this means that these all values are known to us at 0th level for this domain here. So, based on these values, we can just compute all the values in this level here. So, this method is specifically known as a Smith's method, and people are broadly using this explicit method for the computation of different differential equations in a one dimensional sense or in two dimensional sense. And if you just formulate this molecule for this system here, then our system is written in the form of like u I j plus 1 r u I minus 1 j plus 1 minus 2 r plus r here. So, since we are just defining this domain as in the form of like, if this is the domain here, then we will have these points like I minus 1, I and I plus 1 here, and jth level it is just starting like since t equals to 0 it is just starting, then t equals to 1, then t equals to 2, or we can just write t equals to 0, this is del t, this is 2 delta t, likewise it is just moving. So, that is why at a fast level, if you will just see here, these coefficients are written as I minus 1, I and I plus 1 here. And suppose if you will just consider like j equals to 0, suppose here 0th level. So, 0th level means this all values are known to us, and we are just computing this level value here. So, that is why this is called the molecule here. Molecule means we can just consider these 3 values at a particular time to get this value here. This means that this level of computation requires at best 3 different points with the coefficients to get the values. If it is asked the question like del u by del t equals to del square u by del x square, x lies between 0 to 1 and t greater than 0 with the boundary conditions u of 0 t equals to u of 1 t equals to 1 here, with this initial conditions as u of x 0 equals to 1 plus 2 x along this half of this domain and 3 minus 2 x as other half of this domain. If you just see here that the domain is defined in this form, that your range is going from 0 to 1 here, like if you just define x 0 equals to 0 here and x n equals to 1 here, and one particular level it is just considered as like half here. So, where if you just see the boundary condition, it is just given as 1 plus 2 x for this region, and this region it is just written as 3 minus 2 x. And at this point if you just see, this is nothing but if you will put x here as half here, then you can just, this is getting as 2 here, and especially if you just put this condition also here, you can just find that 3 minus 2 into half here, this is nothing but 2 here. So, that is why this represents a symmetricity along the center line there, and the boundary condition it is defined as 0 of u of 0 t, that is nothing but along the first boundary it is defined as 1, and at the last boundary it is defined as 1 of t equals to 1 here also. So, for this if you will just use this space length as 0.2, since it is given, and your time scale it is just given as 0.02, then we can compute this calculation up to like t equals to 0.24. So, up to 6 decimal places it is just asked. So, the problem is symmetric at x equals to 0.5 if you will just put. Now, the domain is divided into 5 sub intervals if you will just see here. So, your u value will start as u equals to 0 at x equals to 0, and it will ended like a final point, that is x equals to 1.0, you will have u equals to 1 there. Since the grid spacing is defined as 0.2 here, so the total domain, that is 0 to 1, will be subdivided into 5 sub intervals, each of length like 0.2. Hence, if you will just consider here like x0 as the 0 point here, then your starting point like x1, this can be written as x0 plus 0.2, that will just give you as x0 is 0 here, 0 plus 0.2, that is nothing but 0.2 here. So, that is the first point here. If your starting point is like x0 here, then x1, x2, x3, x4, and final point is like x5 here. So, that is why we have just defined xi equals to 0.2 into I here. I is varying from 0 to 5 here. So, due to symmetry, as we have told that if you will just consider like x equals to 0.5 here, then we can just find for all j as u of 0j equals to u of 5j, since the symmetry is occurring at 0.5 here. So, that is why we can just consider u of 0j equals to u of 5j here, then u of 1j equals to u of 4j, then u of 2j equals to u of 3j. So, likewise we can just find the values. And if you will just see this r value as here, r can be defined as del t by del x square. So, which can be written as 0.02 by 0.04, since del x is chosen as 0.2 here and del t as 0.02. So, that is why this r value can be find out as 0.5 here. So, if you will just use this explicit formula for r equals to 0.5, then the complete formula it is just written as u I of j plus 1, this can be written as r u I minus 1 j plus 1 minus 2 r u I j plus r u I plus 1 j here. This expression in the form of like u I j plus 1, this is like half of u I minus 1 j plus u I j plus 1, I equals to 1 to 2 here. Then we will have like this boundary conditions that is defined as u of 0 0 as u of 5 0, that is nothing but 1 here, and u of 1 0, that is u of 4 0, that is 1.4 here, and u of 2 0, u of 3 0, that is nothing but 1.8 here. So, at if you just start this computation, then we can just find these values are in this form like 0.00, 0.02, 0.04, 0.06. These are all like time increments we can just get, and your space increments you can just get it as 0, 0.2, 0.4, 0.6 and 0.8, and last point is 1.0 here. And if you just go for this computation of these values by putting this molecules here, so then you can just find this solution as like first point it is a boundary values it is just given like x0 it is just satisfied all these boundary conditions. So, that is just defined in the form of like u of 0 t, and last boundary you can just also find the same value, that is as 1 also there. So, that is why we can just write this as like 1.0, 1.0, 1.0, 1.0 here, and this is also 1.0, 1.0, 1.0 here. And if you will just see this further calculation, so it can just take this boundary conditions there. So, first value we are just getting 1.4, then second one we are just getting 1.8, third we can just, if you just use the symmetricity here, 0.2 remains the same for 0.8 here, and 0.4 is remains same for 0.6. So, likewise if you just compute, so this is the complete table that we can just get all the solutions. Thank you for listening this lecture.